In this video, we will analyze how a IL relaxation oscillator works. First of all, let's draw the circuit diagram. So we have an operational amplifier, which has minus and positive input terminals. And this is output. Similar to the RC relaxation oscillator, there needs to be a positive feedback. So we have one resistor and another resistor on the feedback loop. They are connected to the positive terminal. We call this is R1, this is R2. And then there will be inductors and resistors on the negative feedback loop. So here we will have a inductor, which is L, connected with a resistor. Let's call it R3. And then they are connected to the negative input. So we have a few voltages here. We have output voltage VO. We have input voltage V minus, input voltage V plus. Now we would like to understand how this oscillator works, how it generates oscillating signals. First of all, let's draw the voltage as a function of time. For the output voltage V0, we know since it has positive feedback, usually it will go either to the positive V supply or negative V supply. So this is positive Vs, and this is negative Vs. So now let's first look at what V plus is. Let's assume VO, the output voltage, is saturated at positive supply voltage. If VO is equal to positive Vs, let's draw the VO, which is here, then V plus, since it's on the feedback loop, we can easily calculate its value. Its value is R1 divided by R1 plus R2 times VO, which is Vs. So now we can correspondingly draw the position of V plus. So it will be somewhere here, whose value is R1 divided by R1 plus R2 Vs. Next, let's consider what happens to V minus. Since V minus is also on the feedback loop, there is a resistor and an inductor. So for simplicity, let's draw the equivalent circuit. The voltage comes from the output voltage, so which is positive Vs, that comes from VO. And then we have the inductor and resistor, which is connected to ground. So this is R3. We realize that the input voltage of V minus is actually also the voltage across R3. So this is V minus. We realize that this is a simple first order IL circuit. We can utilize what we learned on IL circuit to analyze its time evolution. So let's assume a simple case that is initially V minus is equal to 0. So, and then we can also analyze what is the final state. We know the final state is when the circuit is fully charged up. So all the voltage is be distributed upon R3. So now V minus will be equal to V plus, positive Vs. Now we can draw its trace in the time domain, which is simply like this. Okay, so now we have the voltage for V plus, which is orange line. We have the voltage for V minus, which is represented by the red line. We notice that there is a point where V plus and V minus cross each other. So we know when V minus start to become larger than V plus, then the input V plus minus V minus becomes smaller than 0. So that means for this comparator, the output VO will turn into negative supply voltage. It will be saturated at negative maximum voltage. So now things will change. So first of all, the supply voltage will go down to completely the negative maximum value. In the meantime, it's easy to see that V plus, since it's directly on the feedback loop, it will also be negative R1 divided by R1 plus R2 times Vs, as it's directly proportional to VO. So now this is V plus, this is V plus. The V plus also becomes a negative value. If the output voltage goes from positive V plus, Vs to negative Vs, you'll notice that this inductor will start to be charged in the opposite direction. Now let's look at the equivalent circuit for this R3L circuit. So again, for V minus, the equivalent circuit is still a simple RL circuit. The only difference compared with the previous case, which is here, is that the voltage source now becomes minus Vs. So the inductor gets charged in opposite direction. Still, we can analyze the initial state, which is the state we obtained in the last stage, which is V minus equal to R1 divided by R1 plus R2 Vs, which is the same as V plus, because that's a cross point. And then we can also easily know what is the final state. The final state is when this circuit is fully charged up, so there is no more variation in the current. So all the voltage is distributed across R3. So now the final state for V minus is just simply minus Vs. Again, we can write out the expression for the time dependence of V minus, but here we will only show it graphically. So it should follow this curve. Again, we realize that when V minus crosses with V plus, that is for the comparator, its output state will also be changed again. So the next state is when the output voltage will become fully positive Vs. And correspondingly, V plus will again becomes R1 over R2, R1 over R1 plus R2 multiply Vs, and inductors will get charged up in the opposite direction again, following this exponential relationship. So this process keep on happening again and again. So whenever V minus catches up with V plus, the output state of comparator will change. So it will go from positive to negative or negative to positive. So this keeps on happening again and again. So V plus always oscillate between positive R1 divided by R1 plus R2 Vs and negative R1 divided by R1 plus R2 Vs, while V minus oscillate also between those two different states. So here, let's get some more quantitative determination of those voltages as well as the periods. First of all, let's ask, what is the amplitude? For the output voltage, V minus as well as V plus. From our sketch, we can easily determine that the peak-to-peak value for VO is simply 2 Vs, because it goes from positive Vs and negative Vs. And V plus, the peak-to-peak value is also easy to determine, because it goes from positive R1 divided by R1 plus R2 to negative R1 divided by R1 plus R2. So this is its peak-to-peak value. And for negative input, V minus peak-to-peak value, that's also similar. That is 2R1 divided by R1 plus R2 times Vs. So this is amplitude of the output signal. And we can also determine what is the period. In order to determine the period, we need to write out an analytical expression for V minus evolution within half a period. Now let's consider this half a period specifically. So we have the initial condition, as we just analyzed. The initial condition for V minus, which is at this point, is it being equal to V plus, which is R1 divided by R1 plus R2 Vs. And we also have its final state, which is get fully charged up in the negative direction. So V minus should be equal to minus Vs. Now we can write out the analytical expression for V minus t. It should be easily just the initial state plus the final state minus initial state and times this exponential time evolution behavior, which is 1 minus e2 minus t over tau. Of course, here tau is a RL circuit time constant, which is equal to L over R. You can simplify this expression, rearrange it. You can get minus Vs plus 2R1 plus R2 divided by R1 plus R2 e2 minus t over tau. So this is the expression for the time dependence of V minus within this period. We know this half a period ends when V minus t, let's call this t0, being equal to minus R1 divided by R1 plus R2 times Vs, because that's where the minus input voltage and positive input voltage cross each other. Then, by utilizing equation 1 and equation 2, you can determine that this T0 So we go through this process, we can easily calculate that this T0 is equal to tau, is equal to tau times log 2R1 plus R2 divided by R2. So that is the amount of time for V minus to go from the positive R1 plus R1 divided by R1 plus R2 Vs value to the negative value. We can also observe that in this circuit, actually, this is only half of the period, and the other half of the period is completely symmetric. So we can, using this result, we can finally arrive that the period is equal to 2t0, which is equal to 2 tau times log 2R1 plus R2 divided by R2. And here, again, tau is equal to L over R. So this is a period for RL relaxation oscillator. Let's put in some real numbers inside and calculate what is the period can be. Let's say if R2, R1 are all 1 kilo ohm, and L is 1 millihenry, and R3 is also 1 kilo ohm. Now, substituting those numbers into the expression of period, we will get T equals 2 times L over R. L is 1 millihenry. R is 1 kilo ohm times log 2 times 1 kilo ohm plus 1 kilo ohm divided by 1 kilo ohm. So this is 3. You have log 3 times this value. Finally, you can calculate. This is approximately equal to 2 2.2 microsecond. So you will get a 50 kilohertz, almost 50 kilohertz oscillator utilizing those values.